Have you ever really thought about speed and velocity? I mean, they kind of sound like the same thing, don't they? Well, in physics, they're actually worlds apart. Today, we're going to unravel the whole mystery of motion, and I promise you, by the end of this, you'll see a race car in a whole new light. All right, get ready for a bit of a mind bender. Picture this, a race car at the Daytona 500. It's just flying around that track, averaging over 160 miles per hour for 500 long miles. That's some serious speed, right? But what if I told you its average velocity for the whole race is a big, fat zero? How is that even possible? Stick with me, because we're about to break down this amazing paradox. So, how do we even begin to solve this puzzle? Well, it all starts with one fundamental concept in physics, the difference between things called scalars and vectors. Once you get this, trust me, the whole world of motion just clicks into place. This is really the key to everything we're going to talk about. Okay, so what on earth are scalars and vectors? It's actually pretty simple. A scalar just has a magnitude, a size or an amount. Think about things like distance or speed or mass. It's just a number. But a vector has both magnitude and direction. So it's not just how fast, but which way. This is super important for things like velocity and acceleration. That little detail, direction, makes all the difference. All right, let's take that idea of scalars and vectors and see how it plays out in the real world. We'll start with how we measure movement. This is where it gets really interesting, because we're going to look at distance versus displacement. They sound similar, but they're not the same thing at all. So, distance is a scalar. It's the total length of the path you travel, how much ground you've actually covered. But displacement, that's a vector. It's all about your change in position from start to finish, and it includes a direction. It's basically asking, how far are you now from where you started and in which direction? Let's make this super clear with an example. Imagine you're walking to school and it's 50 kilometers north. The distance you've traveled is, 50 kilometers. And your displacement is also 50 kilometers. But you have to add the direction, 50 kilometers north. So far, so good. They seem pretty similar. Okay, but now you walk back home. What's your total distance traveled for the day? Well, 50 kilometers there, 50 kilometers back. That's 100 kilometers total. But what's your displacement? You ended up right back where you started. So your total displacement is 0. And that is the light bulb moment. You're starting to see how this connects back to our race car, right? All right, now that we've got a handle on distance and displacement, we are ready to tackle the big one, speed versus velocity. And this is where we finally solve that racing paradox. So here it is, laid out nice and simple. Speed is the rate of change of distance. It's a scalar, so it doesn't care about direction. It's just how fast. Velocity, on the other hand, is the rate of change of displacement. It's a vector, which means it absolutely cares about direction. It's how fast and in what direction. The formula says it all. Speed is distance over time, while velocity is displacement over time. Okay, so this is where it all comes together. Let's apply this directly to our race car problem and finally put this puzzle to rest. First up, let's calculate the car's average speed. Remember, speed uses distance. The total distance was 500 miles. Let's say the race took about 3.1 hours. So 500 miles divided by 3.1 hours gives us an average speed of about 161 miles per hour. That sounds about right, doesn't it? But now, let's calculate the average velocity. Velocity uses displacement. And what was the car's total displacement? Well, it started at the starting line, and it finished at the same starting line. So its displacement is 0 miles. And 0 divided by 3.1 hours is, you guessed it, 0 miles per hour. There it is. The paradox is solved. Okay, so we've got speed and velocity down. But what happens when velocity itself starts to change? Well, that's where our next big concept comes in. Acceleration. So what is acceleration? Simply put, it's the rate of change of velocity. And this is really important because velocity is a vector. If you change its magnitude, the speed, or its direction, you are accelerating. Now, most of us think acceleration just means speeding up. But in physics, that's only part of the story. You're accelerating if you speed up, for sure. But you're also accelerating if you slow down. That's just negative acceleration. And this is the one people often forget. You're also accelerating if you just change direction. Think about a Ferris wheel. It might be turning at a nice, constant speed, But are you accelerating? Absolutely, because your direction is constantly changing as you go around in that circle. So even with a constant speed, there's constant acceleration. It's a perfect example. And if you want to calculate acceleration, it's pretty straightforward. You just need to find the initial velocity, then find the final velocity. You calculate the change between them, and then you just divide that change by the amount of time it took. That's it. That gives you the acceleration. All right, we have covered a lot of ground today. So let's just quickly recap the key takeaways to make sure everything is crystal clear. So, what are the core differences to remember? First, scalar versus vector. Scalar is just magnitude, while vector has magnitude plus direction. Then, distance versus displacement. Distance is the total path you covered, while displacement is just the change from your start to your finish. That leads us to speed versus velocity. Speed is based on distance, so it's a scalar. Velocity is based on displacement, making it a vector. And finally, acceleration is any change in velocity, whether that's speed, direction, or both. And there you have it. Speed, velocity, acceleration. They're not just abstract terms from a physics book. They are the fundamental principles that describe all the motion around us, from a car on the highway to planets orbiting the sun. Hopefully things are a little clearer now. Thanks so much for joining me. For more concept clarity, be sure to join Eclassopedia.